All right, so you have learned about the cell membrane, its structure and function, fluid mosaic model, selectively permeable, phospholipid bilayer. You've learned how things move, how they diffuse along their electrochemical gradient, so from an area of higher concentration to an area of lower concentration. You've learned how things can move across a cell membrane, and the special properties of water and osmosis of water, or the movement of water. So many times in science, we want to either be able to predict or understand why water is moving from one area to another. And so water potential is another formula on your formula sheet. And so this is something that you would use on your AP Bio test. And it's relatively simple. It's going to show you how water moves into or out of a cell. You just need to define these little terms and know how to get to them. So this first little symbol stands for water potential. And water potential is pressure potential plus solute potential. So it's really simple. What is pressure potential? Pressure potential is the amount of pressure that's exerted on water. So if it's an open beaker sitting in a room, there's no pressure. But plant cells will have some pressure potential because remember, to keep them turgid and keep the plant standing upright, they like a hypotonic environment. And so the water enters the cell and it causes the cell to swell and push against the cell wall. Since the cell wall is pushing on the water within the cell, then there's going to be a pressure potential for that. But then they would have to give you that amount. They would have to give you that value, or you'd have to be able to find that value given everything else. But in an open beaker sitting on a table somewhere, pressure potential is going to be 0. Solute potential has to do, it's also called osmotic potential, but solute potential, it measures the effect of the solute on the direction of the water movement. Solute potential is either going to be a 0 or a negative number. The more negative that number it is, the more solute is added to the solution. So in an open air system, so like a beaker just sitting out in the open, with no active pressure generation on it, nothing is pressing on that water, then the pressure potential is 0, and the water potential depends entirely on the solute potential. Pressure potential in the plant cell, remember, is affected by the cell wall, and it's going to push against to prevent any more water uptake. Solute potential, as solute is added, the value for solute potential becomes more negative, causing the water potential to become more negative. So the more negative the number is, the more negative water potential is, and so the less likely water has the potential to move, the less likely it is to move. All right, so for an example, I have a beaker, and in this beaker we have distilled water. Distilled water, that means pure water, so there's no solute in it. It's an open beaker sitting out on the table, so there's no pressure potential and no solute potential. So I know that this distilled water has a water potential of 0 because there's 0 pressure potential, 0 solute potential. The beet core, so this is like a beet and a bunch of plant cells, they are giving us a pressure potential of 0.4, and they're giving us a solute potential of negative 0.4. Remember that the formula for water potential is water potential equals pressure potential plus solute potential. So 0.4 plus a negative 0.4 gives me 0. I already know distilled water has a water potential of 0. Now the beet core has a water potential of 0. That means that this solution and the cells in the solution, these are in a dynamic equilibrium. So the beet core is isotonic to the distilled water. The distilled water is isotonic to the beet core, because remember we have to compare them. So there's a dynamic equilibrium. Water molecules are still moving back and forth, but they're moving back and forth equally. So there's no net movement in one direction or another. So the water potential for this would be 0. All right. So in this other example over here, distilled water, I know that's still going to be a water potential of 0 because there's no pressure potential. There's no solute potential because there's no solute in pure water. But this beet core is a little different. its pressure potential is 0.2, and its solute potential is still the same, negative 0.4. So obviously this beet core hasn't been sitting in this water for long enough for the water to move in and fill up those cells and make them turgid to press against the cell wall and increase that cell pressure. So now 0.2 minus, or plus, so water potential is water potential equals pressure potential plus solute potential. So that's a 0.2 plus a negative 0.4. And that gives me a total water potential of a negative 0.2. So, because it's a negative 0.2, then I know that that water is going to move from the hypotonic environment, which is 0, into the into the beet cells, which have more solute in them, which have less water potential. So the water potential of this is 0. The water potential of the beet core is a negative 2. This is a more negative number than this. So this has less water potential, and the water is less likely to move out of the beet core into the distilled water. This has a bigger number, so the 0 is bigger than a negative 2. So this has more water potential, and so that water has more potential to move from outside into the beet core. So sometimes you're not given things as simply as that. Sometimes you have to find what the solute potential is. This formula for solute potential is also on your formula sheet. Solute potential equals negative ICRT. One of the biggest mistakes that students make is they leave off that negative. It's very important that you do not leave off that negative. I is an ionization constant. So that means it's going to be a given number. The solutes that we most commonly use are sugar and salt. And in fact, in this class, those are the only two that you're going to use. Your solute is either going to be sugar or salt. If it's sugar, if the solute that you're using is sugar, then that ionization constant is a 1. That number for sugar will always be 1 here. If it tells you that the solute is salt or sodium chloride, then the ionization constant is 2. It will always be 2 for salt and 1 for sugar. These are the only two that we're going to use, but know that there are other solutes that could possibly be in solution. We just don't need to worry about those. This talks about how they dissolve in solution. Sugar dissolves just into smaller C6H12O6 molecules, whereas sodium chloride, it's going to dissolve into sodium ions and chlorine ions, and that's why that's a 2 and this is a 1. The C stands for molar concentration. So you're either given the concentration or you have to find the molar concentration. The R is a pressure constant. This is another constant, and so this number is the same. And for us, it will always be 0.0831. That will always be the pressure constant. So that number that goes in here is always going to be 0.0831. And finally, T represents temperature, but it's temperature in Kelvin. So in order to find temperature in Kelvin, you have to add whatever the temperature in Celsius is plus 273 degrees. So Kelvin temperature is Celsius plus 273. Distilled water, pressure potential 0, solute potential 0, so water potential is 0. This is kind of like the beet core. This would be the first beaker that we saw. After being in there for a certain amount of time, the water builds up. It causes a pressure potential against the cell wall. And so the pressure potential will equal the solute potential. And so the water potential will be 0. And so this is in a dynamic equilibrium. This would be like the second beet core picture that we saw previously. And so it's immediately put in the cell. And so the environment was hypotonic to the beet cell, so the water moved in. The plant cell, had less water potential than the distilled water. So the plant cell had less water potential than the solution it was in, so the water moved into the cell. All right, some example problems. Molar concentration of a sugar solution in an open beaker has been determined to be 0.3 molar. Calculate the solute potential at 27 degrees Celsius. Round your answer to the nearest hundredth. So the first thing that you need to do is you need to decide which of those two equations do you need to use. Do you use the water potential equation, water potential equals pressure potential plus solute potential, or do you use the solute potential equation, negative ICRT? Because it's telling us to calculate the solute potential, then I know I need to use the one to find solute potential, which is negative ICRT. Negative, don't drop the negative. I is my ionization constant. Because the solute that we're using here is sugar, then that number is always going to be 1. C is the molar concentration. They give us the molar concentration of 0.3 molar. R is our constant, and that's always going to be 0.0831. That's our pressure constant. And then T is temperature, which is degrees Celsius plus 273. Then all you have to do is the math. So add this stuff up first, then multiply straight across. Don't forget your negative symbol, and the solute potential for this situation is negative 7.479. And they should have rounded to the nearest hundredth, but they did not, did they? Oh, I would mark that wrong. So negative 7.48. That's what I noticed right here. There's the round your answer to the nearest 100th. But the pressure potential of the solution open to the air is 0. Since you know the solute potential of the solution, you can now calculate the water potential. So now we need the water potential equation. So water potential is pressure potential plus solute potential. Water potential, my pressure potential is 0 because it is open to the air, so it's just sitting in a beaker somewhere. Solute potential is what we found on the last problem, negative 7.48. And so when I do that simple math, that's my water potential. So the rest of these slides give you a few more examples. And so I would encourage you to go through and work them on your own and see if you can't figure out what's going on. And if you have any questions, then make sure that you let me know. These slides, I'm not going to videotape them here because you can't interact with them. These slides are found on the PowerPoint. And so open up that water potential or cell membrane PowerPoint and run through to the end of that, and that will give you these other example problems.